what it means to be formal definition. When you have data, okay, you've done some tests and you have these data, you have these data values. What we typically do is we assume, we connect the dots and we assume that this is continuous. It's not, because this is discrete data, but we're saying, well, because this is going up, I don't know that this is happening, but I'm guessing that this isn't going down and back up again. So that's what we end up doing when we have something that looks continuous. It may not be. We're just assuming that it's continuous by. All right, now I know you've seen this before, and we're going to play the game again, but there's a reason in this section for talking about points that are actually continuous. You tell me what the limit as x approaches 0 from the right is. 1. I hear 1. So the thing here, and it's the red lights are going to just shine. The thing here to note, though, is that the limit is the same as the value of the function. Okay, that's the important part, that the limit's the value of the function. I'll mention that again. All right, as x approaches 3, what's the limit? 2. In other words, as I'm looking here at 3, as I'm coming from the left, as I'm coming from the right, and the value of the function is also 2. Remember early on, I warned you guys that limits have nothing to do with the exact value of the function maybe. Okay, now we're into, yeah, they can, and so now we see that they actually. And so what I'm looking at here is I'm looking at continuous points. We're going to define continuous points where the limit equals the value of the function. Okay, so in other words, it's easy to see in pictures here that wherever you have a solid dot, meaning that if my limit is going to a solid dot here, then that is still the same as the function. So what about as x approaches 1? There is no limit. So this was kind of a trick. We said, well, last section, there kind of is. There's a left hand and there's a right hand, but there is no plus or minus here. So this does not exist because there. What about as x approaches 2? Yes. So in other words, as I head towards 2 from the left and the right, it is 1. Good. So you're getting this figured out. But notice that the value of the function is actually 2, and these are not equal. So the limit does not, in this case, does not equal. How about 4 from the left, meaning I'm coming this way?
Maybe 2.
Here's 4. As I'm coming this way, I think it'll be 1. But notice the value of the function at 4 is a half, and those are not equal. That's my whole shebang of all this, is the points that are not continuous here. So in other words, not continuous points is x equals 1, x equals 2, and x equals 4. Notice what, if we look at these, this we said the limit does not even exist. At 2, the limit existed, but it was not equal to the value of the function. And at 4, the limit exists, but it wasn't equal to the value of the function. Definition of what it means for a function to be continuous. So if the limit and the value of the functions are equal, and so that's what all this is saying right here. If I'm approaching some value of c, okay, and I have a continuous function here, if this limit is the same as the value of the function, then it's continuous. You can even have continuity going from right-hand side, going from left-hand side, and we say these are continuous endpoints if they're solid. Okay, so that's all that. And so hopefully in your head you're like, okay, so to prove something is continuous, I just simply prove the limit equals the value of the function. And we'll do a couple of those. And here all this is saying is my right-handed and my left-handed limits as I'm approaching this value from the right, as I'm approaching this value from the left. If they equal the value of the function, then we say at that point the function is. All right, so we can have something like this, say this function is continuous even at -2 and 2. In this case, I'm coming from the right-hand side, the left-hand side, so I do have my left continuous and my right continuous. And what you have to be careful, we kind of say things in a way to make things continuous, is we say this is continuous at every domain point. because you can say, well, over here it's not continuous. And hopefully you kind of remember, and we're going to have a little exercise of reminding things of how do you know things are not in a domain. Of course, looking up here, you don't want to take negative square roots, okay? So long as it's in its domain and these points are included, then this is continuous. So how do you test something is continuous? So a function is continuous at some interior point, okay? So there's some point that we're interested in if and only if it meets these three conditions. The value of the function exists at that point. The limit of the function exists, okay, as it approaches that value of c, and the two are equal, okay? Because you can actually have a value where maybe the limit's not even existing. In other words, if your left side and your right side are not equal, okay? So the limit doesn't exist for this value of c, and thus these two pieces couldn't be equal. So a function is continuous on an interval if and only if it is continuous at every single point in the particular interval, okay? It may not be a completely continuous function, but if I'm only looking, I mean, think of rational functions where you usually have, one going this way, one going this way. Well, if I'm only looking in this bottom left quadrant, I can say it's continuous there, okay? And that's kind of what we're saying here. And then a continuous function is one that is continuous at every point of its domain. It need not be continuous on every. So that's kind of what I was just doing with my hands, is when you look at this, if I say as x is approaching 0, well, you can see the big jump, and we're going to probably get there today where we move to infinite limits and say, well, what's actually happening as I'm approaching from this way? Well, the function's heading to minus infinity. As I'm approaching this way, the function's heading to infinity, but it's continuous everywhere else except at x equals 0. Okay, so if I only care about, say, this first quadrant, then I can say, well, yeah, this function is continuous. And that maybe I'm doing some experiment that I only care about these positive values, and so I like continuous functions because, as you're going to see, there's a lot of properties that you can do things with. All right, so the only continuous function in all these graphs is this first one. Why? Because a continuous function, I can take my pencil and draw the function and never lift my pencil up. Here, I draw it, and oops, I have to jump over and continue to go. Here, I actually have to jump up, okay? Here is definitely a jump. Here, I'm heading off to infinity, and here's my 1 over x that's just simply going crazy. So here, all we're saying as each one of these approaches, as x approaches 0, the only reason why this one is continuous is because as I approach 0, my limit is equal to the value of my function. This, there is a limit there, okay, the limit's still 1. This, there is a limit there, the limit's still 1. This has a left hand and a right hand limit. This one, again, will be next section where we actually do have infinite limits as the same as this last one here. All right, so at what point is the function discontinuous? From what you remember from domains and all that good stuff, this is discontinuous. I heard a 2 at x equals 2. Okay, and you know that from probably algebra because that value is not in your domain. Now, in my math lab, they may ask you this first, and then they ask you to give the interval in which it's continuous. And so that would just simply be your negative infinity to 2, union 2 to infinity. And you will see this little union on the toolbar over there on the left. Okay, so this is how it would want you to answer a question like that. Tell me where it's discontinuous, and then tell me the interval where it's actually continuous. All right, so how about what you remember of your trig? Where is this discontinuous? Very good. Pi over 2, and then we could get crazy and say also 3 pi over 2, 6 pi over 2, and all that good stuff. And so in other words, what he remembered is that if I plug pi over 2 in there, cosine of pi over 2 is 0, and I can't divide by 0. I don't remember how my math lab asked this one, if it was like multiple choice or if you just simply put pi over 2, if you had to put the other values as well. All right, Theorem 8, something that should look familiar to you. In other words, when we first talked about limits, we said that we could simply, if one function has one limit, another function has another limit, we could add the limits. Well, this is the same with continuous functions. If this function's continuous and this function's continuous, if we add them together, it's still a continuous function. We're going to actually do an example with this here with the quotient, that if the top's continuous and the bottom's continuous, then the entire quotient's continuous. And so that's all this says, which reminds me, I did put a theorem, Chapter 2 theorems, and it's all the theorems from this chapter in Blackboard, so that might be something. All right, inverse functions and continuity. If a function is continuous, then its inverse is continuous. Probably most students right away think of inverses, logs, and exponentials, okay? So kind of makes sense with that. Composite functions, f of g, all composites of continuous functions are continuous. In other words, if I have a continuous function composed within another function, then the entire function is still continuous. So something like this, and again, this is why I say this section's kind of weird, is show that this function is continuous in its domain. Well, what you do is you find the two composed functions, which I don't really care about all this other junk. I just see that this is an x squared. Is x squared a continuous function? Yeah, I mean, just look like that, right? And this just has some shifting going on. So this is continuous. And is the square root continuous? Yeah, I mean, it's a continuous. And notice right there, that's the key, in its domain. Well, in my math lab, what they want you to do then is, in this case, where it would not be in the domain, would of course be where that piece is less than 0. Okay? In other words, where you're dividing by -1. But this is a continuous, and I should say this is continuous on 0, to infinity. And a lot of these, minus infinity to infinity, a lot of these, that's what it just asks. It asks, where is x squared minus 2x minus 5 continuous? And again, the little infinity signs over there in the toolbar. In this case, this one just asks for each piece. So it'd be the minus infinity and infinity, and then the 0 to infinity. All right, here's another one. Look at each piece here. I think x is continuous. That's a straight line. Sine of x is continuous. Remember, it looks like that. And we just said this is continuous. Is the absolute value continuous? Yes. Okay, so in this case, all we're saying, and then the question may be, is this function continuous? And yes, because back to that theorem 8, the quotient of continuous functions is continuous. I know it's kind of weird in a math class to prove something with just words, but that's it. That if you can say each piece here is continuous and it's composed within this absolute value, then the quotient is continuous as well.
What about for imaginary numbers? Do you just assume that?
You just imagine that they're continuous.
Because technically that, if you...
In other words, because if you're thinking, let's think of the quadratic formula, and if you end up with the imaginary, so the quadratic formula either has that, it has that, but you're saying it could have this as well, because that would be an imaginary solution, right? So yeah, certainly you could have imaginary solutions being continuous. Isn't that a continuous function? So yes, you could. Yes. I was trying to be funny of imagine it. And then I could go into singing John Lennon Imagine. And then we could talk more about the Texans.
That's all of them.
All right, limits of continuous functions. I did notice there's a couple of problems in my math lab with these, and all this is saying is if your function g is continuous at a particular point, then your limit of your f of x as x approaches c equals b by simply taking, all you're doing here is taking this limit and bringing it inside Okay, so inside this function, well, we must have a pop quiz today. Too many of y'all are here. So that's all this theorem is telling you, but you have to be careful that your functions are continuous. Yes, you're kind of in a perfect world in a math class. It's not like I would mess with your head and give you something like this and then you find out it's not even a continuous function. But you have to make sure that it is continuous. Something like this, technically you're supposed to, sine continuous, this whole thing continuous, cosine's definitely continuous. Now I can proceed. And technically that's what you're supposed to do first. Make sure all of these are continuous. With proceeding now, I mean I can take this limit and bring it inside. So I'm going to have equals the cosine of the limit of 2x as x approaches pi over 2 plus the limit of sine of 3 pi over 2 plus x, all that's in that parentheses, as x approaches pi over 2. Okay, and again, if you can plug in pi over 2, if you couldn't, let's say there was some reason you couldn't plug in pi over 2, like you'd be dividing by 0, then you got to do one of your other techniques. Okay, meaning that either multiply by conjugates, look at the left-hand, right-hand limits. Okay, the problems could be more difficult than this, but in this case, I can just simply plug in. It's going to be 2 times pi over 2 plus the sine of 3 pi over 2 plus pi. That's supposed to be a parentheses over 2. And so I end up with cosine, let's just go to a parentheses now, plus this piece right here becomes the sine of 4 pi over 2, which becomes the sine of 2 pi, which is what? What's the sine of 2 pi? 0, yeah. So this whole piece becomes 0. Okay, so 3 pi plus pi is 4 pi, and then divide.
Is this a formula for something?
Say that again?
Is this by chance like a formula for something?
For something in particular?
Yeah.
What do you think?
I recognize this. I don't remember from like the.
You're going to see it again. Yes, good memory. Wow. All right, and so then what's the cosine of pi? I'm not going to tell you. -1. Which reminds me, I'm not telling you the formula because you're going to have to be able to recognize it later. This reminds me, though, on your test, I realize your calculator can find the cosine of pi, but if there's something that I want exact answers, either have a unit circle on you, have something that I can say there probably will be some questions that will have trig stuff on it, okay, on the test. So be sure you have a way that you can find these values. So when I was looking at my math lab last night, I said, well, there's this problem in there as well. So I thought, well, this could be kind of interesting to do. But this one, notice it says find the limit, and then it wants to know if the function is continuous at the point being approached, which is that 0. Okay? So hopefully I've gotten through to you this morning. How you would do that is you would find the limit and see if it equals the value of the function. So again, to find this limit, I'm just simply going to bring my limit of t to 0 inside. So limit t to 0, and then pi over square root of 15 minus 6 cosine 4t. And I will say many of you are probably looking at this and saying, why is she going all this trouble? I could just plug it in straight here. It's actually a theorem that tells you can do that, okay? That previous theorem, that you can't just do this unless you know, once again, that this is continuous and this is continuous, again, in its domain, okay? And we always kind of throw that piece out there. So now here, if I finish this, I'm just simply going to have, if I plug in 0, get another color going here. If I plug in 0 here, then I get the cosine of 0, okay, which is 1. And then 15 minus 6, which is 9. and the square root of 9, which is 3. So in other words, I just did a whole bunch of steps at once. So all I did was plug in this 0, and then I'm going to end up with the sine of pi over 3. Anybody remember that one?
Square root of 3 over 2.
Very, you must have had a good pre-cal teacher that made you memorize this stuff. Very good. All right, so this is that answer. This is the part where it'll feel weird, because what you're actually doing now to say if it's continuous, you're doing the same thing. So, and this will not always work this way. Sometimes with your limits, as I mentioned before, you might have to do something different this step. Like I see a square root, I may have had to do something with conjugates if I couldn't plug that 0 in. Well, here it's continuous if f of 0 equals this limit. Well, f of 0 in this case means just simply take this function here, and where I see a t, plug in 0. Well, that's what I did on the limit up above. 6 cosine 4 times 0, which is still sine of pi over 3, which does equal this. So this proves that it is continuous because the limit equals the value of the function. Now, again, I know a lot of you are sitting there thinking, well, it always would, wouldn't it? Well, no, because your limit may not be so nice up here. It might be that your limit up here, in fact, we'll do something later where you're having to do a left-hand side and a right-hand side, and they're not equal. So that value is not going to equal, the value of the function is not going to actually equal your limit. But this one in your homework is nice and does this way. All right, continuous extension to a point. So if I have this graph and I say, well, the limit as x approaches 0, in this case is 1, but the value of the function, I don't have the value. In other words, I don't have my f of 0 here. I don't know what it equals because this is open. In this case, what I can do is I can define a new function, and I can say, well, let f of 0, in other words, I just colored the circle in, okay? And this is kind of going back to the very first slide that I showed. When you have discrete data, and you say, well, it appears it's going this way, it also, I can define this as my limit. As my limit is approaching 0, the value of the function is getting close to 1, so why not just call it 1? And so that's all we're doing here, a function, and say, okay, is this function continuous? No. How can I make it continuous? First, why would I want to make it continuous? Because then we have all those nice rules that we can use, okay, all those theorems. Well, how I would make this continuous, this is continuous in its domain. What's the discontinuous point? X not equal 0. So that's my point of discontinuity. How do I make it continuous? I let my x, as x approaches 0, I let it equal the value of my limit. So it's, you know, again, it's kind of one of those, really, that's it, just color in the circle, yeah. I mean, because what you're doing is you're finding what the limit of the function's going to, and you're calling that the actual value, okay, at that actual point. So it's just make these, to make a function continuous, and of course this is something if you don't have a whole bunch of jumps and holes going on, you know, you probably can't do something with that. But now we can say this function is continuous at x equals 0 because this limit of this function actually equals the value of the function because we did that right there. All right, give an example of a function f of x that is continuous for all values of x except for x equals 2. Right now your brain should go to anything with x minus 2 in the denominator. And where it has removable discontinuity, explain how you know that that it is discontinuous at this point. What you do to make it continuous. So if I have, again, I could have made up any function here. I just picked a function that I know the denominator. If I plug into, it's discontinuous at x equals 2. Okay, so that's all I did. And so I say, well, I could make this a continuous function by defining the limit as x is approaching 2. So if I actually found what is the limit of this as x is approaching 2, and I defined that, I actually defined that as the value of the function, then I would make it continuous. Anybody know what that number is? Yes, I'm looking at you because you're answering all my questions. You're thinking? Think about that whole sine theta over theta thing. One, yeah, it works the same. So that's how I could make this a continuous function. It's just simply color in that little circle right there and make, and again, I want you to get the point of why we want continuous functions. There's lots of things in this entire class that we can do with functions only if they're continuous, okay? We can't do a lot of functions. All right, the intermediate value theorem for continuous functions. Again, I don't know, maybe I think, students are getting smarter and you look at stuff like this and it's like a duh. If I'm starting and I'm saying even my endpoints are continuous, I start here and I have a continuous function. I can draw a line, a y equals function anywhere between those endpoints, and I'm going to hit that function. Right? I mean, that's like, to me, a duh, because if this function is continuous, then it would make sense that I would hit these lines, okay? So now, hopefully, you're thinking, well, who cares? What's the big deal? This is a really important theorem, because if you notice, if I draw a line here, I can pick this function up and kind of shift it and call, get back my black, I can call, say, this line right here. Why not call it the x-axis? Why would you want to do that? One of the big reasons for the intermediate value theorem is to find roots, okay? If you have your calculator, okay, we're going to do something to make sure you can do it in your calculators. All right, so that's all this is saying, is that if there's no jumps in the function, it's continuous, I can find this value here, okay, by simply using this intermediate. If there is a jump, then as you can see, I can find a y equals, say, 2.6, whatever in this case. I can find other lines. Because this is not a continuous function, then the intermediate value theorem doesn't apply. So once again, something else, why we like continuous functions, we use this for finding roots. Okay, that's one of the biggest application of this. Now notice this only says this will give the existence of a number, and it doesn't tell us, in other words, is how many points. Think about this. If I have a graph that looks like this, it's not going to tell me that I have this many roots. It's just going to tell me that, yes, I do. Okay? And in this case, we're going to actually find one. And so we're going to use this to find roots or zeros and x-intercepts and with this function. So what I want you to do now is I want you to graph that function in your calculators. Okay, so x times x minus 2 squared minus 2. This will be, I probably get this emailed the most in my math lab, so I want to make sure you can do, there's 2 problems, the very last 2. And it says using the intermediate value theorem. So basically what you're looking for is you're looking for where it's hitting this axis, the x-axis. You're looking for the root. All right, and then it says, if so, use a graphing calculator. The part if so is the key here. Once again, that's continuous and that's continuous, okay? I probably would not, I'm not out to trick you guys and give you something that's not going to be continuous. I might do something in homework to get you to recognize it, but you need to make sure this checks out first. Otherwise, you can't even use this intermediate graph. Certainly those are continuous. Hopefully, and if you have an Inspire, I cannot help you. Somebody in my other class came up and they're wonderful calculators. Wish I owned one, but I don't know how to use it. I'm sorry. If you have an 89, then you're going to click the F5 and 0. And students were looking for 0. It's the word 0. If you have an 83, do second trace 0. Now, it's kind of weird to tell you you're doing to the left and the right. What you're doing is after you do this, you move your arrow to the right, in other words, of your x-intercept. You move it to the left, and you press enter. Okay, after each one, I should have said the left first. You do it to the left of the intercept, the right of the intercept, and then as it will give you in the bottom left corner, it will give you that value. Anybody got it yet? Very good. Okay. So if this is something you cannot get your, sit there and play with it a couple of minutes. If you cannot get your calculator to give you this value, then you definitely should stay after class, because this is something that you will have like I said, you have 2 questions in my math lab. They're the last 2. So basically all you're doing is you're just finding the zeros in this case, and you're telling it to find it around that root. Okay, so you're trying to figure out, and that's why you're going to the left and you're going to the right. Of course, the closer you get, a program like this one online will actually let me zoom in far enough to get the number of decimals that my math lab wants. Somebody asked